let's dive into the third day of our lecture. And I hope you still remember what you did yesterday. It's only one day since we stopped. What was it that we talked on Monday? So on Monday, November, what is Wednesday? On Monday we talked about finite kinematics. So finite kinematics of the kinematic chain, in a sense that you want to know the pose of a rigid body as part of a kinematic chain. Okay, when I say pose, then it means like the orientation and the position due to, and when I say kinematic chain, then we mean a chain consisting of bodies and joints. So the motion of a body due to the joint motion. Okay, so that was what we did on Monday. Yesterday we looked into the velocities. So how can we get the velocity of one of the members of the kinematic chain when we get the velocity of the joints, okay, the motion of the joints. And that's all kinematics, right? And today we will have half kinematics dynamics. And the part of kinematics that we are still missing is what about accelerations, in the sense that what about the time derivative of the velocity? And remember the velocity we call it the twist, right? So we call it the combined vector that comprises the omega and the angular and the linear velocity. We call this the twist. Okay, and this is what we do probably today. Just to remind you what we kind of did yesterday, or what we had been doing. It's good to remind you because it's all new and I guess it's good to remember. So we call a vector that is a 6 vector, we call it the screw. In particular, a screw coordinates if it is going into the exponential mapping. And it consists of the first 3 vector and the second 3 vector. The first one is describing the orientation, I mean the rotational motion. So essentially it's the scaled rotation axis times angle, if you want to say. And the other one is something else. Okay, this is anyway, this is what goes into this vector. And then we had this homogeneous transformation matrix that perform frame transformations, and frame transformation of points. So essentially we use them to represent the pose of a frame, which means the pose of a rigid body. Okay? Okay. And then, so what does this do? This transforms point coordinates from one frame to the other. Let's say we have a point coordinate or a point measured in the frame F, then we get it in the frame F prime. It's the other way around actually. Let's say we have it in F prime and we get it in the frame F if we apply this homogeneous transformation H. And the same goes on the level of twists. That means like velocities and screw coordinates, in a sense that if you have a screw coordinate, let's say a twist measured, like omega and v, measured in this frame, you get it transformed into this frame by applying what you call the adjoint transformation. And the adjoint transformation, if you have a matrix H, that should be H actually instead of C, sorry. And if you have matrix H, then you plug this, I mean the components of H, which is R and little r, in here, and then that transforms actually the coordinate, the screw coordinates or the twist from here to here. Okay. And when I say twist, I mean just maybe to get you all on the same page. I mean, let's say this body is somehow moving in space, so it has an angular velocity that is invariant. I mean, the angular velocity is the same at every point, but the linear velocity, of course, is different. So when you measure it here, it's of course different from here. And that's what actually the adjoint transformation is doing. It changes not only the frame in which you're representing the vectors, but it also changes the magnitude of the linear velocity. Okay, this is what we did. Yeah. So okay, another question could be, yeah, we don't need this. So the question could be, what is actually the time derivative? Oh, I don't have it here actually. Anyway, so we had this v vector, right? So this twist vector, and the question now is, what's the time derivative of this twist vector? Not sure what I'm doing, but should be okay. And this is the topic. Before we go into this topic, we need one more, let's say, mathematical operation or object, which is, let me call it the generalized cross product. Let's maybe just dive into it and say, what if you want to take the cross product of, as I was saying actually, so the first component here is representing rotations, right? Let's say you have two twists, two screw coordinates. So there's one component that describes the orientation and the other one in the second thing. And you take the cross product of the two 3 vectors, and this goes like this. So what I'm kind of saying is that, let's imagine you take a cross product, okay, of the 3 vectors, the C1, C2. Can we generalize this to some sort of a product, maybe not a cross product, maybe spatial cross product, call it, of the 6 vectors? I mean, for 6 vectors, there is no cross product as such, right? I mean, it doesn't really make sense. But there is something that is called the screw product, and that's defined like this. So essentially, I was too fast. There's an equality sign in here. There must be an equal sign in here. I'm sorry, there must be an equal sign in there. Because what comes out of this is, of course, this. So this is equal to this, okay? So there's a lot of mathematics behind it, but we can't go into this because otherwise we have no time and we need much more background on this. But you can accept it, that there's an operation. And there's an operation that takes these two screw vectors, the 6 vectors, and gives you this one. And the first part is just the cross product of the angular parts of the screw coordinates, okay? And the second one, this one, is something different. It's the cross product of essentially this guy and this guy minus the cross product of this one and this one. When I say minus, it's the same like plus if I swap these arguments, okay? What I've been saying, I mean, if you want to remember this, it's pretty simple. The first part is the cross product of this and this, and the second part is the cross product of this and this, minus the cross product of this and this. So the last one was minus C2 cos eta 1. And that's the same like if you take, because the cross product is skew-symmetric, it's the same like minus, which gets you plus eta 1 cos C2. So essentially this is what we call the spatial cross product, but to be more precise, it's called the screw product, and to be even more precise, this is called the Lie bracket for reasons that go beyond the course. But anyway, again, this name Lie turns up, right? And don't pronounce it lie, because it's not a lie, it's true. And you can, of course, now if you look at this, here's an equal sign, right? So if you look at this kind of definition, first of all, what you see is that this term is linear in C2 and eta, C2 and eta 2, okay? Because this is linear in C2, this is linear in C2, and this is linear in eta 2. And every time there is some linear, expression is linear in some factors, you can write it as matrix times vector, okay? And that's what we do here. So essentially, and how do we do this? By expressing this cross product as the tilde times the vector. Just maybe also to remind you about this, when we have a cross product, let's say a vector A cross B, so what we do is then, instead of saying A cross B, we say we plug this vector A into this skew-symmetric matrix and multiply it with B, and this gives you the same, okay? And this was this skew-symmetric 3 times 3 matrix. Okay, that's what we did yesterday. Okay, there's not much more to say because we are not deriving it. But anyway, there must be some names for that, right? So first of all, it's called the Lie bracket, and maybe you call it the screw product, which also makes sense. And to have a name, or let's say a symbol for that 4 times 4 matrix here, we give it a name, and it's called the little adx, the little adjoint. Remember we had the big adjoint, that was just the one I mentioned, that was the one here, that was the big ad. So the big ad takes, this should be H. The big adjoint operator takes a homogeneous matrix, right? And you know, and you form this. The Lie bracket, I mean this little adjoint, takes a screw vector as argument, right? I mean as a parameter. Okay, that's it. So, and that's it. So essentially by expressing this screw product, because what you get here, if you multiply it out, is C dot tilde C2, which is the cross product, and here you get eta 1 tilde cross times C2, which is exactly the cross product here, plus this times that, which is the cross product of C1 eta 1, eta 2. Okay, there we go. And if you look at this expression, for example, of course it is skew symmetric in the arguments, in a sense. If you swap 1 and 2, you get exactly the negative of this thing. I mean, this apparently is skew symmetric because it's a cross product. Yeah, it gives you, if you swap them, it gives you negative. And the same is here. If you change 1 and 2, it gives you exactly the same, because then we have eta 2 C1, which is exactly the one here, so it's all a negative. And the conclusion is that this is the skew symmetric operation. Okay, there are more. Yeah, there are more properties actually of this. There is, for example, the skew symmetry we already had. Then it's bilinear, in a sense that if you take the which one now? If you take the Lie bracket of two screws x and y, and if you say now I take the screw of AI, sorry, if the Lie bracket of the screw screw x multiplied with a, and the screw y multiplied with b is the same as equal to the screw bracket, the Lie bracket, that means the screw product of x and y multiplied with a and b. And that's obvious from just the definition, right? If you have a and b just multiplied with a, of course it goes out, and the same is here. Because if you multiply C1 and eta 1 with a, then you can take it out, and the same with the second argument. Okay, and then there's some something you might, I don't know, maybe this is so-called Jacobi identity. Huh? And it is true for the cross product, yeah. So maybe it's good to remember this also. Where do you know it from? When you have like what if you take the cross product of two vectors? Like you take A cross B cross C, for example. What can you say about this? You can say many things, right? But there is this Jacobi identity, which says, and now this is the thing. See, one advantage of having this skew symmetric matrix, this tilde operator, is that it's actually clear what this means. Okay, what I'm saying is, well, here it's always clear because it's the cross product, right? But what does this mean actually? Do you know? I mean, do you know what? How do you evaluate this? Is it clear to you?
We have equation for it.
It's not clear to me.
If we have an equation for it.
Now, what I mean is, how would you compute this? I mean, you have three vectors. You have two cross products. How would you evaluate this? I mean, literally. I mean, how would you do it? Would you say?
Because we will have a vector perpendicular vector to AB, and with that perpendicular vector with multiple take.
Oh right. So what you're saying is you take the cross product of A and B,
and then multiply the cross.
And then take the cross product with C. Okay. Someone else maybe would have said the opposite, because it doesn't say, right? Because here it is not clear. Because it could also have been like this. Someone could have said, but that's not the same. They're different. Now, when you take the tilde operator, for example, then it's clear because it would be A, B, and C, and you know exactly what it means. Because it means, does it mean like this? Is it, or is it the other one that you said at the beginning? See, here it's all that's why it's a bit of beauty here. The beauty of this tilde operator is it's absolutely clear what it means, because you have a matrix times a matrix times C. So you can even take A tilde, B tilde, and then multiply with C, which is the same as saying, okay, I take this term here, I take B tilde C, this gives you a vector, and multiply with a matrix. So it's all the same. That's what I'm saying. So it's unique. There's a unique meaning. Whereas here you have to set brackets, otherwise you don't know what. By the way, if you want to have like A cross B cross C, how would you write this with the tilde matrix? Huh? Do you mean like this? Yeah, but I was just saying that this is not the same. Okay, literally. Okay, what if you take cross products and you replace the cross products with the tilde matrix? This means that just the argument that is on the left-hand side goes into the tilde matrix, right? Which would in this case mean that you have A cross B tilde C, which is of course different. And you can of course write this as A tilde B tilde C, right? Yeah. And of course you can change this. I mean, I don't know, just maybe a little exercise. That of course is the same. Sorry, this is that's of course the same as saying this is C tilde minus C tilde A cross B, which is the same like C tilde A tilde B, right? Okay, yeah, so why I'm actually started doing, looking into this is because this Jacobi identity, maybe you had it in one of your courses, not sure, because you find this in textbooks on vector algebra, for example. Like the question is, if you take now, and this is what we had here, if you take the double cross product of A, B, and C, which is now A cross B cross C, okay? And the thing is that if you just do even permutations, in a sense that you just, you have like a FIFO loop, so this goes in, this goes out, so you just turn them around, so you have like B, C, A, right? So you just do this, what's the name for that operation? I don't know. And you do it again, right? So you go one further, you have like C tilde, A tilde, B. That the sum of all these is 0. And that's something that you, I don't know, maybe have learned in your course on vector algebra, that you take cross products and 3 of them, and in this form, then this is all 0. And that's called the Jacobi identity. And this is the same here, because as I was saying, I mean, essentially, this is a kind of a spatial cross product. In a sense, it's a generalization of a cross product. If you say this in a 3D version would be y cross x, y cross z cross x. And here it would be the cross product of z and x, cross product with y, and so on, right? And that's exactly what we have here. Okay, there's one more operation, one more property, which is the one here. Maybe this is not at the moment so important. Okay. Maybe this is not so important at the moment. We will come back to this when we need it. Yeah, it's now off. Okay. Yeah. So there's one thing, I'll just give it to you. Because the question could be, and the question will be, what if you take, so we have this adjoint operator, right? We have been saying that this is the one that you get like here, right? So this is the adjoint operator when we have the h in here, and this is it. Now we know that every h, I mean, the homogeneous matrix can be represented as an exponential of a screw coordinate, right? So this is So this is equal to the exponential of x of t, for example. Okay? And the question could then be, if this is so, yeah, here. The question now, if this is h, right, expressed as the exponential of t times x, what's the derivative of this operation with respect to t? And what comes out is this. Just believe it. We can show it, but that's a bit beyond. Yeah, so it essentially repeats it. So the derivative of this adjoint transformation is just, again, the adjoint transformation, but left multiplied with this this matrix that we call the little adjoint, that gives you the Lie bracket or the screw product. Okay. And now it's pretty straightforward actually to ask, okay, what about the time derivative of the twist? What about the v dot? And of course we have to say which twist. And we said that we have two ways of actually describing or representing the twist. There are many ways, but we looked at two. One is the body fix and one is the spatial representation. And we use the body fix simply because it's beneficial for dynamics and so on. Yeah, so take the derivative. So we know that the velocity was, maybe it should be written again somewhere. If you remember the, this is why yesterday we introduced this Jacobian, because the twist of the twist of body I maybe there's a bit of a loose connection here. So what we said yesterday is that if we want to compute the twist of body I in our kinematic chain, then we can do this by taking our Jacobian, which depends on the joint coordinates, I mean the joint angles, times the time derivative of our joint angles, right? We call it joint velocities. And what was this matrix? The matrix was just, you know, yeah, this is JI. And the matrix, we said, was the one that consists of, well, we have so many columns. You know, we have n columns because this is an n vector, so this goes till in, okay? Which is the same like writing, of course, this here as, because what happens is that you multiply q1 dot with this first column and q2 dot with the second column and so on. So essentially this is the same like saying this is the first column, no, don't take the other way around. Yeah, the first column times q dot and so on, which is the same as saying we multiply this with the 1 to n with q dot, qj dot. So we actually do sum over the columns multiplied with the respective q dot. And that's fine. So, and if you take now the time derivative of this, because this is what we're interested in, we take the time derivative of our twist, and then of course it gives you, well, essentially it gives you what we have here. So you take the partial derivative, I mean, first of all you take the time derivative of the q double dot, so this is just repeating itself with q double dot, and then you have to take the time derivative of j. And the time derivative of j, maybe this is what we should write, the time derivative of ji is what? The time derivative of ji is of course simply applying the chain rule, right? Because what you have to do, you have to take the partial derivative with respect to, okay, we need to say k, qk of ji, okay, multiplied with qk dot. So this gives you the time derivative, because what is it then? J depends on q and q depends on t. So taking the time derivative of j is just partial with respect to q times q dot. Okay, now what is actually the, on which, that's what we had yesterday also, on what coordinate, or I mean on what component, or others we're saying, on which joint angles does the Jacobian of body I depend on? What I'm asking is, which of the partials is 0? Or the other way asking, how far I have to go with this sum? Should it be n? So should we have n here?
The number of joint. The number of joint.
Yes, I mean this is correct. But the question is, do we have to go until n? Do we have to go up to n? So do we have to take the partials of J, I, this is the Jacobian of body I, with respect to all the joint angles? So which leads us to the question, on which joint coordinates does the Jacobian of body I in the kinematic chain depend? And so I had the picture yesterday, but it's easy to, maybe we just, so let's say we have our kinematic chain, right? So we have the first joint, then we have the second joint, and so on, right? Just like this, okay? So, and so on, and so on. And let's say we are here. So this is our body I. No, this is a joint, sorry. This is body I, for example, okay? So this is joint I. There's I minus 1, and so on, okay? And this is body I minus 1. And that would be I plus 1, for example, okay? So if I look at body I, which is this one here, on which joint coordinates does it depend?
The previous one.
On all the joints that come along the chain towards the ground. So this means that actually, if you take the partials, then you only have to take the partial derivatives with respect to up to well, let me go again. To I, okay? So from K to I. I mean, you wouldn't have made a mistake if you would have done up to n, but they are 0. So this is a bit of work that you don't have to do. Okay. Yeah, and I guess there we go. What's going on here? I don't know. Yeah. And exactly, so, and remember that we said, how do we get this is what we had yesterday. How do we define, or what was the result for the column J of our Jacobian of body I? It was saying that we only have to take the screw coordinates of the joint J. So the column J, right, the J's column in the Jacobian is the screw coordinate of the joint J, transformed into the body frame I. And that of course goes via the transformation from J to I, because H transforms from J to I, and the adjoint transformation transforms the corresponding joint screw coordinates. Okay? And that was the definition of the Jacobian column. Okay? And if you now take the partial of this Jacobian, then what we have to take is the partial of this term, right, of the adjoint thing. And by taking this, this property, I mean, by taking into account that this is actually defined by the adjoint transformation, we can actually derive this equation. And also this equation I'll just give to you because it's a bit, it takes too long and it's maybe beyond the course to derive it. But anyway, this is the result. And this is why we need actually this screw product. Because what we have here is that it's a very nice result actually. Because what we get here is the partial derivative of the column J in our Jacobian. You don't have to take, symbolic partial derivatives, or computer algebra systems or something. You don't need this. Because what you get is an explicit algebraic form. Because what it says is, remember, that was the Lie bracket, right? And the Lie bracket was just this very simple expression with the cross product. And the outcome is that if you take the partial derivative of the J's column with respect to the joint coordinate K, it's just the screw product which means the lead bracket of the column J with column K. So you take the two screw coordinates, because in the columns of the Jacobian are the incidental screw coordinates. And what you're doing is that you just take the lead bracket of the J's column with the K's column. And that's it. So this is a purely algebraic way of actually expressing it. And when I say purely algebraic way, it's just because this is the cross product, right? So here's the equal sign. This means that if you now say, okay, the x and x1 and x2 is now the column J and column K, is the same. I mean, the expression is the same. You just take cross product of the first part and this cross product of the first and the second, and that's it. There's no, complicated symbolic manipulation involved in it. And this is easy to implement. And this is what's used these days. Okay. Okay, and now, if you of course sum up the partials, then of course you get the time derivative of q dot, because essentially what we had here was an expression for q dot, and then q dot of course is simply the sum of all these partials times the q dot. Times the q dot. Okay. And there we go. And if you do a bit of mathematics and use this expression that I had before, we can show that this is actually the same like this. I just give this to you because it's too much to maybe to have it here. But we are going to use it later on, and later on it will be more compact in all the equations. Well, how to explain this? I don't know. That's what comes out. But let's use this expression, because the j dot, that expression for j dot is again quite beneficial. I mean, if you believe me that this is true, then we can again formulate this in a bigger compact form for the system Jacobian. So the system Jacobian was the one where we have all the Jacobians, right? So the system Jacobian. What was the system Jacobian? That was the one that we have so this J, the big system Jacobian, was the one where we have first the Jacobian for the body 1, body 2, body up to n, right? So it's a 6n times 6n times n matrix, okay? And remember that we had this factorization for this system Jacobian. The system Jacobian, if you remember, was essentially this one. So the system Jacobian, J was equal to A times X. That is what we came up with, if you remember. And now I'm interested in the time derivative of the system Jacobian. And I can use this result for the Jacobian of body I. And I look at this equation here, okay? So the time derivative of the, let's say body 1. So I is equal to 1, okay? So what you have to do is what? You have to go here from, so this is the double sum actually, right? So the indices, they go from, so K goes from J plus 1 to I, okay? So J for, if I is 1, then J can only be 1. Because the Jacobian of the first body, that means the velocity of the first body only depends on the first link, right? Okay, if J is 1, then K must be bigger than 1. But if K is bigger than 1, which means that K is bigger than I, then this is 0. Which means that essentially the first partial derivative is 0. But if you look at the next one, how to explain it best? Yeah, and then you get the identity matrix here. And then essentially what you get, so what I'm trying to get at is the first one. So this is supposedly the time derivative of the first Jacobian, which is the identity times q double times q1 dot times the adjoint of x1. Okay? Times j1. Okay? So this is what you get here. This is exactly if you express this for the first joint, for the first body. And if you go to the second body, you get one more term, which is of course this adjoint, because now you have k equal 1 in the first column. You have always k equal 1. Then you have I equal 1 equal 2, for example, and then you have the two summation terms. And then what you get is this term times q1 dot times you know, x1, and then the identity times this, plus of course always the joint, the Jacobian. And by the way, I have to excuse myself because for some reason I still have the C instead of H. So C is H here. So all the C, all the H, I mean all the C's are H. Yeah, yeah. I mean, this is just when you write this for all the for each of the bodies, and you can write, and you can just multiply out this, and you see this gives you exactly this. But that is actually very interesting because what you get here is again a kind of a matrix form for the derivative, and moreover, what you get here is this we identified already as the A matrix, right? So what you get here is J dot is minus A dot, A, this is this term, right? And then we need the name for this one, and just call this little a, okay? Let's say that we call this matrix little a, this one. And then we have J, times J. If you want to express J as A times X, then it looks like this. So this is just the same. This is just replacing AX by J. And there we go. So this is the time derivative. This is the compact form for the time derivative of the system Jacobian. And that's essentially it. If you haven't followed, don't worry. The outcome is this, and that's what you're going to implement. Okay? The formula is pretty straightforward. Again, we take this A matrix, which is the triangular matrix here. Then we have a new matrix, little a, which is this matrix. That's the diagonal of this 6 times 6 adjoint matrices. And then again AX, or you have already J. And then you can, of course, take the time derivative of the system twist, which is then this. And of course, it's the product rule because V is equal to J times Q. Done. Yep, okay. That's for the time being it. And maybe we should summarize it. What we had so far, because now we looked at velocities and accelerations. And by the way, the term acceleration is not really correct. We should call it the reduced acceleration. Because this v dot is not necessarily the acceleration that you normally understand by taking time derivatives of omega and of v. Anyway, it's what we're going to use. Okay, so just to summarize, this is what we had also yesterday introduced in the velocity, I mean the twist of the body. There is the body fixed version that we introduced with by just saying we take the inverse of the homogeneous transformation from body I to the space fixed frame times the time derivative, and this gives you this form of a matrix. And as we saw yesterday, this 4 times 4 matrix corresponds uniquely to a 6 vector by just taking out the vector here, the linear velocity, and by taking out the vector that's in the symmetric matrix, which is the body fixed angular velocity. And then we have the space fixed version, which we don't really use. Yeah, then we had the twist. The twist is given by, you know, the sum of the columns of the Jacobian. And if you don't want to call them the columns of the Jacobian, you should remember that they are actually the instantaneous screw coordinates of the joints, right? So you just measure you measure the screw coordinate of the joints relative to the frame I, and then you get these. And they are changing in time. I mean, they are changing with the pose of this system. And because they are changing with the pose of the system, we need to have an expression, and that depends on the pose of the relative pose of frame I and frame J. Right? So the frame I is the one of which we are interested in the velocity, and then we look at the joint J, and this is of course changing, and then that's why we have the transformation from I to J. Yes, and these are giving you the columns of the Jacobian of body I. And then we just saw that the partial derivative actually of this Jacobian column is explicitly given in terms of these very simple screw products, or called Lie brackets. Okay, yeah, and having said this, we can actually get the acceleration of the body in terms of the partial derivatives of the Jacobian. But we can also, of course, express all together in a very compact form using the system Jacobian and the system twist. Okay, system twist is that one, the system Jacobian was that one, but just plugging in all the 6 times n Jacobian matrices, so it altogether is a 6n times n matrix. And we have seen yesterday that we can have this very compact form, this factorization of the Jacobian, which is saying that we have A times X, okay? And this matrix A was the one that we have this triangular structure, where we have the identity matrix, the 6 times 6 identity matrix on the diagonal, and we have the transformations here. And again, this is very systematic because this is always transforming from body 1 to, from frame 1 to the frame n. Because what comes out here is the Jacobian of the body 2, body 1 is equal, body 2, body 3, body up to body n. And that's the contribution of joint 1. The contribution of joint 2 to the whole thing is that you have, again, this is the second, third, and up to n, twist that we are interested, contribution to the twist that we are interested in, and this is the contribution of joint 2, and it goes up to, of course, up to the end. And the last one is then the identity, because there's no transformation from n to n. Yeah, that's it. Okay. Good. Yes, and then finally the time derivative. So this was the Jacobian itself. The time derivative is, of course, just what we said. J dot is that equation. Minus a times little a times j. Okay. And if this is so, then we can actually proceed, because this is what we need for the dynamics. Right? Because for the dynamics we need accelerations, and that's essentially it. Yeah, maybe we should, maybe have a look at this. Have you heard of order n algorithms? Recursive order n algorithms? Let's maybe go back. If you want to compute this, question could be, what's the computational effort that you have to do in order to construct the Jacobian and eventually determine the twist of the system? So let's say how many, no, that's not a good question. I could ask, how many operations do you need? I don't know really. You have to depends how you implement it, right? But the question is, how does for one particular implementation, and even if it's the most efficient one, how does it scale with the system size? Like if I have one more joint, how many more operations do I need? Does it go linearly? Does it go quadratically? Does it go, I don't know what, exponentially? You can easily look at just the matrix here, for example, right? So let's say I have one more joint, which means one more body.
16 element.
Huh?
16 element gets added.
Yeah. So essentially, because it's a square matrix, right? You will need, how to say? Well, because it's a square matrix, it goes quadratically. Right, this is what I want to say. But this is not the end, because once you have done this, you have to multiply it with q dot. How many operations do you need? N operations. So again, this scales, there's one more order, because you have to this is quadratic in the effort, and then this of course goes, again, linear, there's one more power, so to say, in this effort, it goes cubically, right? So the number of operations goes with the power of 3 with the number of joints. And even if it's a super efficient implementation, it doesn't change. Because whatever you do, even if you do it efficiently, it goes with the power of 3, increases. And that, of course, is for long kinematic chains, is not efficient. In particular, for example, remember this human body model, right? You can say, well, my robot has 6 degrees of freedom, why do I care? But if you look, for example, in systems with many joints, for example, the human body model, right, you have so many joints, and at one point you make it more complicated, more detailed, right? If you have a high fidelity model, you have more joints in it and so on. And then, of course, you're going to have a bit of an issue, maybe, if you want to do it online, in real time, and all this, right? And that's why people invented this, their so-called No, it doesn't say. It's the so-called order n algorithm, in the sense that what I was saying is actually the number of operation, and they write it like this, it scales with order n 3. So this is how what you find usually, like O of n 3, right? So in this order, it could be anything. And what people are interested in, what people are, I mean, there was a long, of course, development, is order n methods. So it scales linearly, right? So that whenever you have more joints, it goes linearly with this. And you can even ask, is there a way of actually going even lower than like the power of less than 1?
Constant.
Huh?
O of 1. O of 1 operations.
You're correct, this is what I have here, O1. But can you go less than 1?
Maybe constant operations.
It sounds a bit strange. I mean, how can you do this? So what I'm saying is, so usually, I mean, this kind of thing, you take just matrix times vector and so on, it goes cubically, right? I don't know where it starts, somewhere. It goes like the power of 3. Now, the super efficient thing is, it goes linearly. I don't know, somewhere, linearly. Now, there are people actually that developed logarithmic order. So it goes like this. I don't know how it goes. I don't know how it goes. Logarithmic order. Now I'm stuck. I don't know. It's sub-linear somehow. And how can you do this? Because I mean, it's actually not possible, right? If you because whatever you have to compute, you have to compute. So let's say you are somehow able to what is it then? That equation. Just say will twist as a function of q dot. That you increase, you have one more joint. If it is not linear, if it is sublinear, which would mean that actually you have one more joint, but you don't have exactly the same number of operations you have to do. You have less operations to do. It sounds strange. So, okay, the magic point behind it is using parallel computing, right? So you do something in parallel. And now with all this GPU computing, okay, you can do a lot of things. Did anyone use GPUs? How did you use it?
For my machine learning model training.
Machine learning, so you didn't really use it. It's a provocative statement. No, because do you know how it works in the
Yeah,
back?
there are thousands of cores, and you can split the matrix on separate cores.
Yeah.
So all computations are done in parallel and singleton.
Yeah. If you look in detail, it's not that easy actually. It's not that you have like 1,000 or 100 million processors and you can individually give a task to them. This is not working like this. Because they all get the same job.
I do something for CUDA programming also.
Aha, okay, then you know what I'm talking about. It's
on
not
multiple threads, we have to spin the matrix across the threads, and after that, just normal C-like stuff, and the GPU will do the other stuff.
Yeah. Because the GPU is not, I mean, each of the GPU is not like a normal, processor. It's a very special thing.
It's not processor, but it's like function-like thing.
Yeah.
So we can use the not exact like cores. We have one CPUs, but we like verbs and threads, and I forgot the name. Not physical cores, but they can split use virtual RAMs to store the matrix
that's right.
objects.
Yeah, the shared memory stuff.
Shared memory stuff.
Yeah. Anyway, so okay, and there's one easy thing that we can do, and let's maybe look at an possibly efficient order n way of actually at least computing the twist and the acceleration of our system, and that goes recursively. So instead of actually, this is the point, instead of constructing the matrix and then multiplying the matrix with q dot, you could actually capitalize on this kind of equation. And if you look carefully, we can do this recursively. And I just maybe go through it. I left it in the slides, just because. So, but this equation, you could have stated it without actually all this mathematics. Why? Because it has always a physical meaning. And by the way, if you don't see a physical meaning here, then you should raise your hand and see what I did wrong. Because all of this is explainable in the sense that you can even easily have a kinematic meaning. So what does it mean here? I don't know where we start. So this is supposed to be, again, the twist of body I, right? So what is the twist of body I? How do we get it? In terms of the twist of the preceding bodies, as well as the joint that is connecting it to the preceding bodies. So let's say this is, which one? This is body I, right? So body I apparently is, of course, so let's say that the whole thing is somehow moving, right? Whatever it does. So each of the joint, does something. So and let's say we are given already the twist of body I minus 1. Then of course, let's say this joint is locked, right? Then the whole thing does what it does, and this I body is just going along with it. So the only thing we have to say, okay, if I know the twist of body I minus 1, I just have to transform it into the frame of I1 of body I. Because if I have to, so there's a frame here and there's a frame here, right? So I know the body twist of I minus 1. I transform this twist from I minus 1 to body I. And then I have at least the motion, the twist of body I due to the motion of all the predecessors. I have not yet included the joint motion, but that comes later on. And how do I transform the twist? Well, that's very simple. Because what I can do, of course, I'm not sure if people see it actually. Some labor work to do. Okay, let's hopefully get this done. So what I was actually kind of alluding to is, let's say we have this kinematic J with the body 1, body 2, and of course joint 1, joint 2, and so on. And at one point, we are coming to the body I minus 1, okay? That's of course connected to the predecessor by joint I minus 1. And then we have the body I, body I, and there's the joint I. That's a big mess, I hope. Not? Okay. Yeah, so, and what do I know? I know there are frames on it, right? There's a body frame here and there's a body frame here. So what do I know? How do I go from I to I minus 1? Well, we know already, right? That's the transformation we talk about all the time. Because from here to here, you go via H, which one? You see, you don't have to think about it if you just understood the notation. It's just I minus 1 I, right? And that's what we know. And if you don't remember, so Hi minus 1 I is equal to the inverse of H minus 1 Hi, right? So, and this is what we get from the exponential mapping. And what, so this is the frame transformation. This is like the relative pose. We have the rotation and the translation between the bodies. If I have twists of I minus 1 and I, the Vi and the Vi minus 1, then I get Vi from a Vi minus 1, while the accordingly the adjoint transformation, right? So the twist actually is the same. So if I have the twist in I, then I get the twist in I minus 1 by saying I take the adjoint of Hi minus 1 I times Vi exactly, right? So you see, this is doing this Hi minus 1 I is doing the frame transformations. The adjoint of Hi minus 1 I is doing the twist transformations, right? The only thing is that this is not what I want, because I want to know this one if I have given this one. Well, that's easy. You just take the inverse, right? So you just take the inverse of this. And the inverse, by the way, of this one, you can also show this, is the same as the inverse of the argument. Okay, so vi minus 1. Okay, wonderful. What's the inverse of this one? What's the inverse of hi minus 1i? Well, you don't, that's what I'm saying. I mean, once you have understood the notation, well, it's just the opposite. It's the inverse transformation. It's the one that goes from, so this one is actually just hi minus 1. Right? It just goes the other way around. And you get it from here by saying, okay, this is the inverse of I, hi minus 1. And there we go, and this is what you have here. So this is essentially this term here, right? So the first one is just giving you, this first term here is just giving you the twist of body I, where you know the twist of the predecessor, and forget about the relative joint motion. Let's say the joint is locked, right? Then this is it. Because it's simply saying, okay, if the joint is not moving, I mean, if the joint is kind of locked, so if this one is locked, then the two bodies, they form like a virtual body, right? Okay, now that's it. So, and what about the joint motion? I mean, what about the relative velocity that is caused by the joint motion? This one, if this one is moving. Well, this is simple because you need to what do you need to do? Before I do finger pointing, I better dig out a slide from yesterday, because otherwise it's maybe not a good idea. So let's see, yesterday was number 3. Exactly. So, and what we concluded yesterday from this, no, this was not the right one. If you have the two, again, body I minus 1. So the twist of this frame, this means body I, well, due to the motion of the last joint, what is it? It was just this term here, right? It was just the screw coordinate of the joint I expressed in frame I times q dot. What can we say about the screw coordinate of body I, the screw coordinate of joint I expressed in body I? Does it change or does it not change? It's constant, because this joint does not move relative to this frame, because it's just the one with which the body is connected. What I'm saying is that this term is actually xk, as we call it, right? The screw coordinate of the joint I. Okay, and that is exactly what goes into this equation. Because what goes into this equation is exactly this. It's exactly this, what we have here, x times q dot of the last joint. And so this is kind of a recursive way. Now, this is what you do, is you start with, for example, so what you do, you start with the velocity of the first body. What is it then? The first body would be the transformation of the V0. So 0 was the ground. For our systems at the moment, they're not moving. I mean, the ground is not moving. So this is 0. So the first velocity of the first body is just x1 times q dot 1, which makes sense. And then you start, and V2 is then the transformation of this V1 plus, and so on and so on. So what you do is recursively evaluating. Now the question is, if I increase the number of joints, so if I have one more joint, how many more operations do I need? It's time to go? Yeah. How many more operations do we need? 1.
One multiplication and how many choices do you have?
Okay, this was not a good question. My question is, how does it scale? So how many times I need to do what I have to do for each of the joints, and exactly 1. I do the same equation just one more time. So the number, I don't know, it's a certain number you need. But how many more times you need to do this? For one joint, one time. And so it scales linearly. Simply because you have, essentially what you do, you have a loop, right? You start from for I equal to whatever 1 to n, right? And now n is 1, n is n plus 1, it's just 1 more, and so on. So it scales linearly. And that's essentially what we have found. And I learned that we have to stop now. And that's a good idea.